complexity and query evaluation. And today is going to be a shorter day than others. We'll finish by around noon or so. The expectation was that by the afternoon of the fifth day, typically people, might take off to the airport or something. So we give you a bit of free time in the afternoon. And yeah, so the topic of the last day is going to be incremental view maintenance. It's going to be given by Xiao Hu. She is technically an assistant professor at the University of Waterloo, but her visa situation has run into a bit of an issue. So we don't quite know yet. Anyways, yeah, so I'll give the mic to Xiao. Without further ado, please go ahead.
Okay. Hello, everyone. I'm here again, but today I'm talking about incremental view maintenance. I'm afraid that I may not be the best person to talk about this topic because there are so many experts in the audience. But I'm very interested in this topic and I started working on this problem in the last 2 years. So today I would like to share some interesting results in recent papers and hope to give you some idea about the group discussion. Okay. So let's have a quick review of the problem definition. Dan Altino gave us a very nice talk in the bootcamp. So this slide is just from his talk. The basic problem is that given a query and a database, we want to deliver the query answers as soon as possible to the user. And this problem becomes more challenging when the database is dynamic, where the tuples can be inserted and deleted. Then how to compute or maintain the query answers efficiently. And instead of computing everything from scratch after every update, the idea is how to utilize the previous query answers to build the new query answers, The common approach is to build a data structure, by exploring the query information of the query structure as well as the statistics of the database. So that the query answers can be enumerated from this data structure with bounded delay. The delay is the upper bound on the time between the start of the enumeration and the receiving the first answer. Is also upper bound on the waiting time between every consecutive pair of answers, as well as the receiving the last answer and the end of the enumeration process. There are 3 important performance metrics for the data structure. One is the pre-processing time, to build the data structure, and also the update time, to update the data structure when the tuple is inserted or deleted. Lastly is the delay for the enumeration process. In Dan's talk, he focused on the trade-off between these 3 important measurement, the pre-processing time, the update time, and the delay. But in today's talk, I will focus on the constant delay enumeration. The constant means that, the user only needs to wait a constant time before receiving the first answer, as well as the waiting time for receiving the next answer. If the query is just a Boolean query, the constant delay means that the answering time is just a constant. The constant can depend on the size of the query, the number of relations, and the number of attributes. So here we focus on the pre-processing time and the update time for this data structure.
So the goal is not to output the delta. The goal is to build a data structure where you can get the entire view.
That's a good point. Yeah, I plan to distinguish full enumeration and the delta enumeration in the talk. Yeah, that's a good point. So the user can request the full results, the QD, or only the delta results. The delta result means the new result induced by the inserted tuple, or the older result will disappear by the decision of one tuple. So this problem in general is very hard. We learned from that the update time for general queries is at least the root n. And a data structure with a constant update time is only possible if the query is queue hierarchical. Okay. For example, we have two tables, R1AB and R2BC. If we want all attributes to be outputted, then the query is queue hierarchical. But if we are only interested in the attribute A and C in output, then this query is non-queue hierarchical. This is also a landscape, okay, from Dan's talk. If we just focus on the constant delay enumeration, so this is the overview of the results that can be achieved for pre-processing time and update time, okay, for different class of queries. You can see in the middle is the queue hierarchical query, and we can achieve a data structure that can be built in linear pre-processing time and updated in constant time for constant delay enumeration. But for all other queries, we need to pay much more cost. Okay. There are some observations. Okay, the first one is that the class of queue hierarchical query is still very small. Okay, sitting in the middle of the whole picture. And the second observation is that the upper bound on the update time is not very satisfactory. Yeah, if you just look at the queue hierarchical, we can hope for constant. But for free class query, this is linear and similar for hierarchy and the triangle join, as well as the general conjunctive query. So there's still a huge gap between the queue hierarchical and the non-queue hierarchical. And even I don't know whether this is the best we can do. Yeah. The third observation is that the negative result or the hardness result we just talked about, it only holds for the worst case update sequence. The worst case means that you can arbitrarily construct the update sequence. But in the real world application, most update sequences are not so bad. Instead, they display some nice property or patterns. Okay, the question is, can we design better algorithm by exploring the information of the update sequence? If we have more information about the update sequence, can we have a better analysis? So in today's talk, I will first focus on the full enumeration for full conjunctive query. So this is the class of query, okay, in the whole picture. In the second part, I will move to conjunctive query with aggregations. Okay. If we still have time, I plan to go to the delta enumeration, but this part, okay, is optional. Okay. Yeah, I will go through some results in the recent papers. Okay, listed there. Now I will have a quick review of the background knowledge. So the definition of conjunctive query, I usually interpret as the join project query. So you have a bunch of relations in the body of the query and also the set of attributes they are defined on. The output attribute is the subset of attributes that appear in the body of the query. And we also call it a full join if every attribute appearing in the body also appears as the output attribute. And when the output attribute is empty, this is a special Boolean query, which only outputs true or false, indicating whether there exists a join results in the body of this query. Here are some examples. The first one is the Simon's triangle join. You want to output all the triangles in the query. And the second one is length for path, but we're only interested in the first 4 attributes. Okay, and the last one is also is the Boolean query determining whether there exists a length for path. Okay. Yeah.
Do you allow self joins?
When we talk about upper bound, yeah, self join doesn't make a difference. But this is a good question for lower bound. Yeah, I think it's great for discussion. So So what is a free connex query? There are many different definitions here. I just introduced one based on the join tree. Okay, I think you have this in the previous talk. Okay, let me just quickly go through this. Join tree is a tree structure such that there is a one-to-one correspondence between the relations and the nodes. Okay, so if suppose this is the conjunctive query, and we will have R1, R2, R3, R4 as the nodes of the tree. Okay, and for every attribute, all the nodes containing this attribute forms a collective subtree. Okay, you can check. For example, this X2, R1, R2 are connected. For X3, R2, R3 are connected. X4, R3, R4 are connected. Okay. There's another condition for free connex. Okay. This says that no output, non-output attributes appears above the topmost node of any output attribute. Okay, this is a little bit messy here. So we just consider the topmost node of any output any attribute. Then it says that the topmost node of any non-output attribute should not be the ancestor of any the topmost node for any output attribute. Okay, let me show some example here. X5 is non-output attribute. The topmost node, it appears, is R4. For example, X1 is the output attribute, and the topmost node, it appears, is R1. Here, R4 is the ancestor of R1. So this is not a valid join tree for the free connex query. Okay. Okay, similarly, for this one, the connectivity is not satisfied. X3 appears in R3 and R2, and they are not connected.
So, Xiao, the free connex, is it the property of the query or property of the tree? It is that there should exist one joint tree with this property.
Yes. Yeah, you can interpret this as R1, R2, R3. This collected subtree, including this root, forms a connex of this tree. Yeah.
So sorry. So which one is the output attribute here?
X1, X2, X3, X4.
Okay.
So those are the output attributes. If it does not appear, X5 is the non-output attribute.
So if you turn around that chain, then it's good. If you draw it upside down.
Exactly. So the join tree is not unique. Yeah.
It's not just unique. It's, it depends how you draw it. Yeah. So I suppose you assume an orientation on the edges.
Yeah. Okay. You can also put R3 as the root. Just the root is this tree. Yeah.
So I might be very wrong, but is there an equivalent definition saying that if you add one more atom containing certain attributes?
Yeah.
So
they are equivalent.
So what is the precise one? Can you remind us?
That definition says, okay, first the query should be acyclic, so there exists a join tree, and if you add another relation, say out, containing all the output attributes with the Q, this is still add another relation there. The resulted query is still acyclic.
So it's conjunction instead of this one. So instead of union, you should have.
Yeah. Sorry, this is not very precise, but I just want to see if you add another relation to this query. Yeah, to the body of the query.
So here, if you add another relation with x1, x2, x3, x4,
yeah,
you need to completely restructure that tree to make it free. I'm assuming you have already.
Yeah, you need another join tree. Yeah.
Okay.
Where you collapse some of the nodes of the original tree.
No, you still need to keep them. You become a star, no?
Yeah, exactly. You have a big one as out, x1, x2, x3, x4, and you have R1, R2, R3,
yeah.
R4. Great. Okay. We talk about the frequency query in a dynamic setting. We need a more complicated join tree. Okay. Now we generalize the previous joint tree by introducing the generalized relation. So the generalized relation can be a proper subset of any original relation in the body of the query. Okay, it is still a tree structure, and yeah, the first three conditions are almost the same. The fourth one is that generalized relation appear above of any original relations. In this example, X3 is a generalized relation. Okay, it could be the projection of R2 or R3. Okay, and it appears of any original relation in this tree. There's another condition says that for every generalized relation and its child, this attribute should be completely contained by the children. There are different definitions of generalized joint tree. I will talk about them later, but this one will be used in our analysis. Okay.
So it says for E and each of its children.
Yeah, each of its children, every children. So you can imagine on top, this is essentially a Q hierarchical. Yeah. An important notion here is the height of the joint tree. Okay, the height of this generalized joint tree is the maximum number of original relations on any leaf to root path. Okay. For this example, any leaf to root path, the number of original relations is just 2. So this generalized joint tree has high 2. There's some nice property about the generalized joint tree. The first one is, okay, how to connect these two Q hierarchical queries. So, okay, Q hierarchical is a very special class of queries that for every attribute, pair of attributes x1, x2, okay, EX is the set of relations containing attribute X. So there is some hierarchy between the set of relations containing these two attributes. Okay? And more importantly, if one attribute is an output attribute, and this EX1 is a true subset, proper subset of EX2, then X2 should also be output attributes. Important observation is that a query is Q hierarchical if and only if it has the height 1 generalized joint tree. Let me give you an example. So for this example, we can I can give you some intuition here. So we can build some tree on the structure on the attributes based on this hierarchy, okay, relation. And if you can look at the height 1 generalized joint tree, you can have some correspondence between this one because you can just put all the nodes from the root to this one and to augment this node, then you will get the corresponding node in a generalized joint tree. And for this one, if you check every leaf to path, root path, there's exactly one original relation. So this tree has height 1.
How did you get that variable already? That tree?
Oh yeah, so so that's what we can get from the hierarchy. Means that if the EX3 is a subset of EX2, you just add X2 as the parent of X3. Okay, so that's the background knowledge. Now we are ready to talk about enumeration for full conjunctive queries. In the literature, the framework change propagation is the traditional way to handle the problem, and each query plan can be represented as a tree such that every original relation is a leaf of this tree, and each internal node is an operator. For example, for this query plan, it will materialize the joint result between R2, R3 as a view V1, and then further materialize R1 join V1 as V2. And also, for example, here, this is the projection operator. It will materialize V3 as the projection of R4 on attribute X4. And later, okay, it will further materialize the join between V2 and V3 as another view. Okay. If there is an update in the original relation, it will propagate to the root. Okay. Since we have materialized V4 is the query result, okay, of this conjunctive query. So the full and the delta enumeration are trivial because you just need to investigate the root node. But materialize these views is very costly. For example, the view V1 can be as large as the size R2 times R3 because they could be a Cartesian product. Also, the update cost can be superlinear. For example, if we want to update the V2, okay, the update time is also superlinear. Okay. And all these expensive costs are caused by the join operator because you keep joining those views and materialize them. So this will increase some superlinear cost. The basic idea of this line of work is to replace the join operator with the semi-join, then followed by a projection operator. So we will introduce two views here. One is for projection and the other for semi-join. For this example, okay, we first have the semi-join view as the original relation. Then we need to pass some information from the bottom to the up. So which information we need to pass, which is exactly the projection of R1 on X2. X2 is the join attribute between R1 and R2. Okay. Yeah. So we also do this for R4. We first materialize R4 as the semi-join, and then when we do bottom up, we just pass the projection to the parent. Okay. Then when we build the semi-join for R2, we need to combine the information between R2 and the projection from R1. So this is the semi-join, which is R2 semi-join VP R1. Okay. After we merge the information, we need to further pass the information upward. So we need another projection on X3, so which is the join attribute between R2 and X3. Okay. Similar. Okay. As the top node, we just do a intersection between the projection view from R2 and R3. Okay. So this example, when we have a formal definition, so for the projection view, it's just a projection of the semi-join view on the common attributes between this node and its parent. Okay. And for the semi-join view, if this is a NIF load, the semi-join view is just the relation itself. But if it is an internal node, the semi-join view, okay, for the original node, for example, the R2 is just the R2 semi-join, a set of projection view from its children, okay? And if it is a generalized node, then the semi-join view is just the intersection of a set of projection views. Okay.
Xiao, this is not the change propagation. This is like a full.
Yeah, because we want to change propagation without joins. Yeah.
No, but what you are describing is not yet the delta computation. This is just the
full enumeration. Yeah, exactly. Okay. So that's good. So good observation is that both semi-join and projection are efficient to update. Okay, for example, for the semi-join, the size of the result will always bounded by the R1, the first relation, and so we can use bounded memory for materialization. And also each update in R2 will cause at most n changes in the result. So we will have a bounded maintenance cost. And also for projection, we know that the result of the projection is at most the input size. So we will have bounded memory for materialization. And also each update can cause at most one change in the result. So we will get a constant update time guarantee. Okay. Now I will show how to maintain this projection view and the semi-join view. Okay. To do that, we need some additional counters. Let me use this example to illustrate that. So for this semi-join view, which is exactly R1, we have this projection view of the projection on X2. We also maintain some counter, okay, which simply just count how many tuples from R1 with the specific join value. Okay, for this 2, there are 2 tuples. Okay, so we just store 2 here, and there are 1 tuple with value 3 here. So we just store 1 here. It's quite simple, just counting. Okay, and when we have the counter for the semi-join view, okay. Suppose this is an internal node with k children, okay? We just maintain the number of children such that the projection of this tuple is valid, means that this exists in the projection view. Okay, let me illustrate in this example. This node will only have 1 child here, so the value of the CT is just 0 or 1, okay? If you just look at this tuple 1, 2, okay? We search whether 1 exists in a projection view. It does not exist. So this value is 0. For this 2 and 2, we search whether 2 exists in a projection view. Yes. Okay, then it's 1. So for this node, this CT value is just 0 or 1. Okay, because it only has 1 child here. Okay. With these 2 counters, we can efficiently maintain the update. Okay, if we have an update from the original relation RE, okay, say R2, and we want to update the semi-join view, it only takes constant time. Okay, and if we have update from the semi-join view, and then we want to update the projection view, okay, this is also efficient, is also easy because we just need to change the CT value here. But if we want to update from this projection view to its parent's semi-join view, we will get into trouble because you will have, for example, in this case, if all the tuples have the same X2 value, then you may cause linear update. Okay. In this semi-join view. If you just change this 2 to some other value, okay, this 2 is deleted or something, is another value inserted, then you have to change this many counters in this table. Okay. So this is the worst case analysis here. Okay. Later we will see how to do better. So there's a big run example, but I think if you don't have question about the previous slides, this run example will become trivial. Okay, we just build this. Okay. I just want to say that even those tuples have CT value 0 means that they should not exist in this semi-join view. We just keep it here. Okay, and I'll use different color. And if we want to do insertion, this is also quite straightforward. We first insert this tuple to the original relation, and then we need to propagate the update to the projection view. Okay. Then we need to update every tuple in the R2, semi-join R2 with the same value 1 here. And later we need to propagate the projection view correspondingly. At last, we need to, there are some new tuples appear in the projection view, then we need to change the CT value here. So the 2 here means how many children nodes such that 1 appears in their projection views. Yeah.
So I'm wondering with these counters, couldn't you just have a single counter per distinct attribute value, and then they all just point to that same field, and then you just update one? Like, let's say, all the ones that have the same x2.
Yes.
Let's say if they have x2 equal to 1, they just point to a single memory cell that has the counter for x2 equal 1. And then you just set that one to 1 or 0, depending on if it exists in the child.
Yes, you can also do that.
So wouldn't that get rid of the O of n update cost, or is there missing something?
You can get rid of. No, if, for example, here is 1, 2, 1, 2, and 1, 4, which will be updated with the insertion. Yeah, because they have different values on X3. Yeah.
So you could not point it. Yeah, I was just thinking, because you don't need the X3 until the next level, but then you need to still connect it.
Because, yeah, for the next level, we want to store X3. Yeah, so that's the issue. Yeah.
In the semi-join views, how do the count zeros get generated? The rows that have CT0?
Yeah.
How did they appear to begin with?
Okay. Because the semi-join view R2 is the semi-join between R2 and a bunch of projection views. So if you don't look at the CT value here, this is exactly the table for R2.
So you just keep it there.
Yeah, we just keep it there. Yeah, yeah.
Okay, but it's not affecting any of the analysis, and it doesn't get any.
Yeah. Yes.
Okay, thanks.
Yeah, I want to understand the semantic of the count. So my mental model for IBM has been that we keep, so you take input relation, and then give it a 1 if it's in the relation and 0 otherwise. So you can understand the semi-ring from Boolean to count. And then this semi-join deduction algorithm will become variable elimination. So you calibrate the tree decomposition, the joint tree. And so this count is effectively when you remove or add something from the children node, you kind of update the view, which is an application query on top of children, right?
Yeah, exactly.
So what is the semantic of this application query? Is it just a, join becomes some product?
I think it's just a Boolean semi-ring, so exists or not. So it's just
okay, so you are not overcounting and then
it
will collapse back to either 0 or
1. We don't do that. Yeah. So this counter, sorry. Yeah, the counter here just to represent whether it exists or not. Yeah. So 2 means that this 1 exists in both projection views. And this 1 only means, okay, it exists in only in 1 children in the projection view of 1 child. So the deletion will be similar. So I think I will just stay here. And when we have the full enumeration, this is not it's not hard because key observation is that the information stored in a semi-join view is exactly the local join result in a subtree rooted at this node. Okay. Yeah. Okay. Then we know that if we look at the root of this tree, okay, the semi-join view is exactly the join result, the projection of the join results on this output on this attribute. Okay. So So we only need to retrieve the query result for each tuple in the semi-join view of this root node, okay, in the top-down manner. This is not Okay. So suppose we have a tuple T here, which is in attribute 3. Then we just use the projection of this tuple to probe the semi-joint view in R2. Suppose we found some tuple T prime, and then we further use the projection of T prime on attribute X2 to further probe the semi-joint view of R1. So so then you can get the result. Yeah. Okay. I also have an example here. Suppose we are interested in this tuple 1 in the semi-joint view. We want to enumerate the query result participated by 1. Then we just go to the semi-joint view of R2 and find the tuple with 1, 1. Yeah, and then go down, find the value with the same value 1 in X2. So we get 1, 1 and 4, 1. Okay. Similarly, we probe this right subtree, and we will further get 2 more results. Okay. Yeah.
If CT is smaller than the number of children, how do we know which child to probe?
They won't appear in the query result. We don't need to.
The column names will tell us.
Yeah.
Okay.
Yeah. The count will tell you whether this is a query result or not. A query result or not. So, do you want to have a break here?
Why did you probe R3 again?
R3, okay. Actually, you can just do independent. You just probe 1 here, and you will get 1, 2. Yeah. So this 1, 1, 1 and 4, 1, 1 is already the result we get from the left subtree. Actually, you can interpret as the Cartesian product between these 2 trees. Right? Yeah.
But can't you have more results coming from?
More result from. If you probe 1, you will check all the tuples with the value 1 here, and also the CT value should be 1. Yeah. So we will get 1, 2. Yeah. So we will stop here because the R4 only contains output attribute X4. X4 is also already covered by the R3. So we will just stop here. Yeah. So I think I will stop here, and I hope you have a basic understanding of the algorithm, and later we will, as well as the worst case running time, update time. And okay, when we are back, we will consider the instance dependent analysis of the algorithm. Okay, and
All right, thank you. Take a 5-minute.